Greetings to all and welcome to this lecture. We are in module 1, review of semiconductor fundamentals, lecture number 5, PN junction part 2. In previous lecture, we have discussed about the fundamental building block of PN junction device and we analyzed the PN junction under equilibrium. We have also seen that what will happen if a forward voltage applied in the PN junction, meaning the P region will be connected to the positive terminal of the battery and N region to be connected to the negative terminal of the battery. In this lecture, we will see what will happen when a reverse bias condition will be applied, meaning you have a PN junction and you are connecting battery in such a way that the negative terminal will be connected to P side and positive terminal will be connected to N side. This is an interesting case as per this course is concerned. We will also see what will happen about the small signal capacitances of PN junction. These are the learning outcomes of this lecture, which helps you to analyze the PN junction under reverse bias condition. This also gives you an idea about the small signal capacitances of PN junction. So let's do a quick recap. In last lecture, we have discussed that when P-type material is combined with N-type material, they form a junction at metallurgical junction, and because of that, the huge amount of hole will go from left to right. Similarly, the electrons will go from right to left. This causes a diffusion current in the PN junction, but this diffusion current is counterbalanced by the drift component, which is nothing but when the hole will leave the P side, it will leave an immobile ions. Similarly, when the electrons go from N to P side, it will leave immobile positive ions, and hence there exists an internal built-in voltage or internal built-in field which causes the drift component. So the diffusion component is counterbalanced by the drift component, and under equilibrium will get no net current out of PN junction. By using this, we also derived a formula of built-in potential, which is nothing but phi bi is equals to phi t log Na Nd by Ni square, which simply says that the built-in potential depend upon the doping of P side and N side materials. By using this formula, we have also derived the junction law, stating that if I know the doping concentration of one side and I want to know the doping concentration of other side, if the potential in between is given, then I can simply write the equation as Pp, which is hole concentration at P side, is equals to hole concentration of N side into exponent of phi bi by phi t. I need to choose whether it is a positive exponent or negative exponent. I can use a common sense that if this is a majority carrier concentration, then it will be higher than the minority carrier concentration, and hence this will be positive exponent. Similarly, if I write Np, then it can be written as Nn e to the power of minus of phi bi by phi t. We have also seen the forward bias case where we said that if we apply a voltage in PN junction in such a way that P region is connected to positive side and N region is connected to the negative side, then there will be a current flowing into the PN junction, which is nothing but a diode current, and given by I equals to I naught e to the power of V by phi t minus 1, where I naught is a reverse saturation current, which we will see in this lecture as well, which flows when you are in reverse bias. So that this equation is also hold good when you are operating the diode in reverse bias. So this is a forward bias, this is a reverse bias, meaning the voltage is negative. We have also seen that in forward bias, the dominant mechanism of the current is due to diffusion, because the barrier gets lower and hence the electrons will be diffused from N side to P side and the holes will diffuse from P side to N side. So the dominant mechanism will be diffusion, which is nothing but given as this is hole diffusion and this is as electron diffusion. But in general, in semiconductor we do have the drift component as well. So this component is the drift component, and similarly this component is the drift component, which can be calculated as the total current minus the diffusion component is nothing but the drift component. We have assumed one approximation that there is no mobile charge carriers present into the depletion region, and that's what we called as depletion approximation. But later we said that this approximation in practical junctions does not hold good, because the current throughout the junction should be constant, and to support this current flowing across the junction, there are some mobile charge carriers present into it. Let's analyze the PN junction under reverse bias, meaning you have an N-type region, you have a P-type region, and you are connecting P-type region with a negative terminal, an N-type region with positive terminal. The moment you connect this, what will happen? The expansion of the depletion region will be more. Why? Because let us consider you have a P and N, and the moment you connect a negative here, positive here, which is nothing but a reverse voltage, this negative terminal attracts all the holes in this side. Similarly, this positive terminal attracts all the electron in this side. So the no carriers are crossing the depletion region. To maintain a charge neutrality and balancing the charge, the depletion region expansion will be more in the reverse bias. If the depletion region expansion will be more, the potential drop here will be more, and this potential drop is now become phi Bi plus Vr. The total voltage across depletion region was phi Bi minus V, but here the total voltage is phi Bi plus Vr. This is here. We can also calculate the space charge width. It means what is the width of the depletion region from here to here. Now we need to consider the total voltage drop across the depletion region, which is nothing but W is equals to square root of 2 into epsilon S divided by Q into V or phi Bi plus Vr 1 over Na plus 1 over Nd. We will explore this in much detail as follows. What will happen to the built-in potential at the junction? Let us analyze this using band diagram. For example, I do have a band diagram of N side. So this is EC and this is a Fermi level at N side. So EFN, this is an intrinsic level, and this is EV. Similarly, when there is no voltage applied, the Fermi level is aligned. So this is EFP, and this is valence band, and this is conduction band. And this bending is nothing but Q into phi Bi. Now let us consider you are applying a reverse voltage. So let me change the color of my pen, which actually tells you how the Fermi level moves. So here this is N type, this is P type. You are applying a negative voltage this side and positive voltage this side. The moment you apply a negative voltage, the energy will increase. So ultimately the new position of Fermi level is like this. This is EFP, and we need to follow, this is the valence band, this is the intrinsic level, and this is the conduction band. So ultimately you can find out the overall barrier height is now increased by what amount? By applied voltage amount. So this is shown here. The total barrier height is get increased, and hence the carriers cannot easily cross the junction, and hence the current will be very, very small. That's what the current, we called it as reverse saturation current. So if this is a diode IV characteristic, so this current is very small, and that is I naught, because I is equals to I naught e to the power of V by phi t minus 1. Now if the applied voltage is negative, then I can write I naught e to the power of minus of Vr by phi t minus 1. If the applied voltage is less than 3 times of phi t, then this exponent can be over. This can bring a current in third quadrant which is negative, when you are increasing the reverse voltage. Let's analyze the PN junction more in terms of capacitance when we are talking about reverse bias. So let us consider you have a PN junction like this, where this is a metallurgical junction. The expansion of the depletion at N plus side is D1 and the expansion of the depletion region at P side is D2. This is P and this is a 3D structure as we have already discussed in previous lecture. So the overall charge in this region is Q1, which is nothing but Q times of Nd times of D1 into area. Similarly, this charge is Q2, which is governed or captured by Na. So minus Q into Na into D2 into area. But under charge neutrality condition, Q1 is equals to minus of Q2, right, which gives Na into D2 is equals to Nd into D1. From this you will get this relation. This is a useful equation when we solve for one step or one-sided junction. Similarly, we can calculate the peak of the electric field by the same charge density profile. So the charge density profile says this is plus Q into Nd expansion at D1. Similarly, this is D2 and minus Q into Na. If I want to calculate the electric field, then the electric field along the X can be calculated by its area. This is nothing but like this. So the peak electric field E peak can be calculated as an area of this by an epsilon. So the total charge Q into Nd into D1 divided by epsilon, or Q into Na into D2 divided by epsilon. Now let's see what will happen when the depletion region expand in different region, and then how the potential drops across in different regions of depletion region occurs. Meaning, if there is positive charge at the N side, this is the charge density profile, you take area or just integrate it, you will get the electric field. So this is an mod of electric field, and you will get the potential by just calculating the area of this triangle. So psi 1, which is the potential drop across the N side of the depletion region, which is nothing but half into E peak into D1. Similarly, the psi 2, which is the potential drop across the depletion region which is available at P side, can be given by the area of this triangle, meaning half E peak into D2, where if I put E peak value, which is nothing but Q into Nd into D1 by epsilon S, you can get this equation. So it is clear that the potential drop is dependent as square of the expansion width of the depletion region. The total potential drop between the overall depletion region can be given by psi 1 plus psi 2, which is nothing but given as psi c. Let us consider the case when we do have one-sided step junction, meaning we considered that this is P and this is N plus. If that is the case, the expansion of the depletion region at N side is very small as well as compared to the expansion of the depletion region at P side. So we can consider the depletion region is expanded only in one direction, and hence the overall built-in potential will drop only across the lightly doped side. Like if Nd is greater than Na, then we can simply say the expansion of D1 is very small as compared to D2. So the psi 1 or the potential drop across D1 is very, very small as compared to the potential drop across psi 2. So psi 2 is nothing but the total voltage drop across the depletion region. So by using this, we can simply rewrite as D2 is equals to 2 into epsilon s into psi 2 divided by q into Na square root, where psi 2 is psi c, as psi 1 is considered to be 0 in one-sided junction. So we will get this equation as D2 is equals to 2 into epsilon s into q into Na into root psi c. Now if we say the charge per unit area, it means we considered only the 2D plane and find out the charge available in this strip. So this area we are dividing and calculating the total charge per unit area. Here the Q dash stands for charge per unit area, which is nothing but Q2 by A. Here this Q2 can be taken from like this. So ultimately it is Q into D2 into Na, where you can put D2 value from here and you will get square root of 2 into Q into Na into epsilon s into root psi s. This is nothing but charge per unit area in the depletion region at P side. It means at lightly doped side. We are going to use this equation extensively when we will talk about the MOS transistor modeling. This equation tells us how the charge of the depletion region related with the potential drop across the depletion region. A few more points on the reverse bias, as when you apply a reverse voltage, then there is a constant saturation current flows, which we called it as reverse saturation current. This reverse saturation current is strongly dependent on temperature. It means it will increase by 7% per degree rise in temperature, meaning when you increase the temperature by 10 degrees, ultimately this gets doubled, right? So the performance parameters of diode or PN junction is strongly dependent on temperature. Let's analyze the small signal capacitance. If you see a PN junction, P and N, and this is a junction, if you see carefully, whenever I am applying a voltage, let's say a reverse voltage, then the charges are separated out. So these are negative charge, these are positive charge, and this junction forms a depletion region. In the depletion region, we said that there are no mobile charge carriers. It means this depletion region can be considered as an insulator layer. This region does have charges which is positive, holes in majority, and this region have the charges negative, electrons in majority. And these two regions, which are called neutral regions, are separated by a depletion region where there are no mobile charge carrier available. So this configuration can be considered as a simple parallel plate capacitor, where one metal is made up of P, another metal is made up of N type of semiconductor, and they are separated by a depletion region. So ultimately I can simply write C is nothing but change in charge per change in voltage. This change in charge per change in voltage give me a small signal capacitances of PN junction. Let's analyze the capacitance or a small signal capacitance of the PN junction under reverse bias. As we know that whenever we are applying a reverse voltage, the charge of the depletion region is increases, meaning the expansion of the depletion region is increases towards this side as well as towards this side. So if we want to write the potential balance equation, which simply says the Q1 at N side is nothing but Q into A into D1 plus delta D1 into ND, where delta d1 is an expansion of this layer. Similarly, I can write q2 is equals to minus of q into a into d2 plus delta d2 into Na. And under charge neutrality, they both are equal, and hence what we will get, q into a into d1 plus q into a into delta d1 into nd is equals to minus of q2. So, q into a into d2 into Na plus q into a into delta d2 to Na. These are equal, so we can simply cancel, and now it shows that this all are equal. It means the change in the charge at the n side is exactly equals the change in the charge at p side. So, to calculate the total capacitance, I can simply write delta of q divided by delta of v, where v is nothing but Vr. Here q I can take either q2 or q1. So, let us take q1. So, you can simply write d of nd divided by dVr into change d of d1, where a very small change in d1 per small change in Vr, considering that this small change approaches 0. So, we can simply replace derivative. Following this, we know how the depletion region thickness at each side related with the voltages. So, d1 can be written as 2 into psi s into phi bi plus Vr in reverse bias case divided by q into Na by Nd into 1 over Na plus Nd square root. When you differentiate with respect to Vr, you will get an expression which simply says Cj, or the junction capacitance, is nothing but Cj0 divided by 1 plus Vr by phi bi, where Cj0 is nothing but, we need to take here per unit area. So, Cj0 is nothing but the capacitance when the Vr voltage is 0, correct. So, this is the junction capacitance exists in the reverse bias case. In general, we can write this equation Cj dash as Cj0 divided by 1 plus Vr by phi bi times alpha j, where alpha is dependent on what type of doping you are doing. If it is an abrupt doping, then we generally take 1 by 2. If it is linearly graded junction, we will take 1 by 3. Now, let us rewrite the junction capacitance equation for one-sided junction. So, we can simply write, in one-sided it is dq2 divided by dVr, where q2 can be taken from this equation, and you need to differentiate with respect to the reverse voltage, which will give you square root of 2 into q into Na into epsilon s divided by 2 times of Vr plus phi bi. So, this is the junction capacitance for a one-sided junction. Here we assume that the doping of N plus is higher than the doping of P. This will give me the overall capacitance of one-sided junction. In a similar way, the capacitance does exist when the diode is in forward bias, but we are not going to discuss in detail about this. Ultimately, when you applied a voltage in a forward bias like this is P side and N side, the depletion region get narrower, and hence there is a charge transfer from one place to another place. So, we can calculate the total change in charge per change in voltage as tau times of di by dv, where I can be rewrite as I naught e to the power of v by phi t, where we are assuming that applied v is greater than phi t, and hence minus 1 term can be ignored. So, this can be tau t into I naught e to the power of v by phi t divided by eta into phi t. Let us consider the eta as non-ideality factor. So, ultimately C will be tau t, the transit time ID diode current into eta by phi t. Correct? Let's solve a problem which is given as we do have an n plus p junction and there is a graph plotted between the junction capacitance per unit area with respect to reverse voltage. Find out the slope of this graph. So, as we just derived, the junction capacitance of one sided junction can be given by 2 into q into epsilon s into Na divided by 2 into Vr plus phi bi. So, this is given as 2 into q into Na into epsilon s divided by 2 into Vr plus phi bi. Let us do something which is comparable to this. So, we are going to do square of this is per unit area is equals to 2 into q into Na into epsilon s divided by 4 times Vr plus Vbi. This is 2. So, ultimately 1 over Cj square is equals to 2 times Vr plus Vbi divided by q into Na into epsilon s. So, if you see, this is nothing but y is equals to mx plus c, where slope m can be given by 2 divided by q into Na into epsilon s, and it is written that the slope of the graph we need to find when the p side is intrinsically doped. It means Na is nothing but what? Ni. Then we can rewrite as 2 into q into Ni epsilon s. So, we know all the parameters related to the silicon, that Ni is 1.5 into 10 to the power of 10, epsilon s 11.6 into 8.854 into 10 to the power of minus 14 farad per centimeter, and this value also we know 1.6 into 10 to the power of minus 19 coulomb. So, likewise we can calculate the slope of this graph. So, let me summarize this lecture. In this lecture we have seen what will happen when a reverse voltage is applied in the PN junction. Reverse voltage means that P side of the PN junction will be connected to the negative terminal and N side will be connected to the positive terminal. We have seen that when we apply a reverse voltage, the depletion region expansion will be there, and to support that there will be a potential drop across this. We have also considered a special case of one-sided junction, considering N is heavily doped and P is lightly doped. So, the expansion region, the depletion region expansion will be much more at the P side. This is the general case what we are going to opt in our MOS transistor modeling. Later we have seen what will happen when you change the voltage by a small amount, then we can get a small signal capacitance of PN junction. We have seen the junction capacitance under two conditions can be given as Cj0 divided by Vr plus Vbi plus 1 under reverse bias, and under forward bias it is diffusion capacitance, which is nothing but tau t into Id divided by eta into phi t. So, we will stop here for today. Until then, take care.